Okay, my apologies. The video cut out due to somebody calling my phone and it being put onto my iPad. I'm sorry. So what we were saying is we want to calculate the variation in the wall shear stress as we move downstream along our boundary layer, along our flat plate. So the shear stress at the wall is, as we've talked about before, is going to be equal to tau wall, which is equal to mu du dy at y equals 0, or at the wall. So if I have a profile of the velocity, then I can compute at y equals 0 what du dy is, and I'll talk to you in a minute about the fact that we can actually compute it from the momentum thickness as well. So here, this plot over here, it's the same kind of idea. I've set my wind tunnel to 5 meters per second, and now I've calculated the wall shear stress. And you can see that at the very leading edge of the wall, we go from a free stream to 0 with the no slip condition, and so we have actually a pretty high shear stress, but very rapidly the shear stress gets quite small. And then when we transition to turbulence, again at about 500,000 for our Reynolds number, then it jumps, the wall shear stress gets very high. So generally, the wall shear stress for turbulent flows is much higher than the wall shear stress for laminar flows. And again, the way that we get this shear stress is if we have a velocity profile, we can take the gradient. And I have these two velocity profiles here that I can basically take a gradient. The other thing that I can do, though, is I can compute it from the momentum thickness if I have a profile. So here, this is really nice, and an important result is given the fact that we know what the momentum thickness is, we can calculate the drag force. So here, the drag force is going to be equal to the integral over our plate. So we have a plate that we're going to go from 0 to some distance L along our plate. So if this is our plate, and this is X, Y, and this is our boundary layer, and we have, some sort of a shear stress that's acting along that wall. So we'll integrate, say, from the leading edge to some point L. And if we integrate that shear stress along the X direction, okay, so we're basically looking at this shear stress on the surface. So we integrate in the X direction, and then of course there's a width here. Then we will end up with the drag force. So the integral of that shear stress on the wall is going to be equal to our drag force. And that's what we're saying here. So the shear stress at the wall, and we'll integrate that times the area. So think about it as a little shear stress element here times the area of the plate that's acting on. And if we do that, actually, it turns out that the drag force can be specified in terms of the momentum thickness. And that is because the shear stress can be specified in terms of the momentum thickness. That is, the shear stress, and that's tau wall, is equal to rho u infinity squared times d theta dx for this. So I'm not going to go through the full derivation of this, but it allows us to immediately be able to calculate if we have a velocity profile, we can calculate the momentum deficit, the momentum thickness. And then if we have it at two locations, then we can calculate the shear stress, so because we need to calculate a derivative from this. So this is a powerful tool, and it should make sense. I mean, this is exactly what we talked about in our derivation, that the drag force on the plate was equal to rho u infinity squared times the width times the momentum thickness. That's just what we used when we used the momentum integral to derive the drag force. And that drag force has to be equal to the shear stress integrated over the flat plate. So this is really nice. It's pretty powerful. And then if we take the derivative of this, we end up with this equation that we have here. We define two different things. So now on a flat plate boundary layer, the only drag that we have that's at play is what we call skin friction drag. And when we talk about skin friction drag, that's exactly the shear stress at the wall that's causing a drag. It's the friction at the wall. We can define two different non-dimensional coefficients. The skin friction coefficient, which is tau wall divided by 1/2 rho u infinity squared, and the drag coefficient related to this friction, which is the drag force divided by 1/2 rho U infinity squared times the area. And again, this area that we're talking about, that we're integrating over, is the surface area of the plate. So if you have, maybe say you have a flat boat, and some kind of a boat with a flat bottom, and the bottom of the boat, the boat has a length of 2 meters and a width of 1 meter, then the surface area that we would have a boundary layer acting on would be the 2 times 1 meter. And so that's because along the bottom, as say the boat's going like this and we're over the water, our boundary layer is forming here down on the bottom. So that area is the surface area that's in contact with the fluid. Actually, a couple other things that I want to do is I want to show you the behavior. Again, when we have non-dimensional parameters like a drag coefficient, we want to understand its functionality against the Reynolds number. We run experiments or we use our analytical solutions. And here what you'll see is for the laminar flow, this is a log-log plot. So actually you'll see that this is linear on a log-log plot, but this power law, which is this drag coefficient is like 1.33 divided by the square root of the Reynolds number. And then for turbulent flows, now remember, transition occurs at about 5 times 10 to the 5th. So the transition's occurring right here at about this Reynolds number. And then generally for turbulent flows, we have a couple of different parameters that we can use. So for turbulent flows that don't have too high of a Reynolds number, we can use this value. Well, and it's the meaning from about 5 times. This will be valid from about, say, 5 times 10 to the 5th to about 10 to the 9th. But if you want to include this is going to be valid for also the high Reynolds numbers that we have. And actually, this Reynolds number, this goes all the way to 10 to the 9th. This one goes to about 10 to the 7th. Sorry. You can see where it's valid in the curve. So 0.0742 over 1/5 root of the Reynolds number is valid from about 5 times 10 to the 5th, or 500,000, to about 10 to the 7th. And then this parameterization down here, the one that's 0.455 divided by log Reynolds number to 258, that's going to be valid all the way to 10 to the 9th. So oftentimes we use this one here because it's just valid over a larger range. The equation that we have here that actually includes this transitional behavior, it combines our high Reynolds number form with a low Reynolds number form. And so this one can be used over this whole range of transitions. So from 5 times 10 to the 4th all the way to 10 to the 9th. So I guess if you only wanted to look at one equation, this one that we have here, you still need 2. You need one for the laminar case and then the transition and turbulent region. But you can combine this equation here with this equation here to cover the full range. Okay, so that kind of describes the behavior of the boundary layer shear stress. Now the next thing that we're going to move on to talk about is pressure gradients. So boundary layers that are exposed to pressure gradients. And so what I want to do is to start out by having a quick look at kind of give you a visual feel for what's going on. So in the top here, we have a favorable pressure gradient. What that means is that the flow is accelerating. So favorable, we'll see, it means that dpdx is less, and so here this is the x direction. Again, this is the y direction. dpdx is less than 0. The flow is accelerating, so that means that du dx is greater than 0. And on the bottom plot, this is an adverse pressure gradient. And in that case, the flow is decelerating, so du dx is less than 0, and dp dx is greater than 0. So we go, in such a case, this is a situation where we go from low pressure, low P, to high P. And up above, we're going from a situation where we're going from high pressure to low pressure. And so you can see that as the flow accelerates, the boundary layer is kind of becomes thinner, and as the flow decelerates, and it's going to decelerate, it's already zero at the wall where we have our no slip condition. You can see that this becomes very, very thick, and actually at some point actually separates from the wall, and that's a key feature that we're going to discuss. So let's take another example of this, and I think I have a YouTube video, hopefully it's queued up, that we can look at here. This is talking about separation and boundary layer transition.
As the angle of attack of an airfoil increases, the flow in the boundary layer stops, then reverses direction. This is called boundary layer separation. As angle of attack increases further, the point of separation moves forward on the airfoil until it has so disturbed the flow around the airfoil that further increases in angle of attack produce less rather than more lift. In this condition, the wing is said to be stalled.
Okay, so in this condition, as he said, we took an airfoil that's a symmetric airfoil, and we started to increase its angle of attack, or the angle with respect to the upstream flow. And it goes, at the very beginning, when the flow was when we had zero angle of attack, we had a region of friction, but as we increase the angle of attack, what ends up happening is we change the pressure gradient, and at some point we get separation, and that means that the flow is no longer able to follow, the streamline is no longer able to follow the surface of the body, and at some point we get what's a massively stalled situation, and the pressure drops greatly over and we have a great pressure differential between the upstream and downstream side. That leads to a drop in lift and obviously a big problem for aircraft, and we will discuss that a little bit later in class. So again, this is our favorable and adverse pressure gradient situation. So what I want to do now is I want to take a minute to talk a little bit more about what I mean by adverse and favorable pressure gradients, and what its impact is on the flow. So let's go ahead and do this, and we'll go ahead and start a new note here for you guys. So the adverse pressure gradient is what we were talking about, but we're talking about just pressure gradients in general. So let's say pressure gradients and boundary layers. Okay, so this is something that's really, really important. But to initially kind of talk about this, so what do we mean? So again, if we have a situation where we have an adverse pressure gradient, and some of this I just want to talk about because it's terminology. And an adverse pressure gradient, this is a situation where the pressure gradient dP dx is greater than zero. Okay, that means that the pressure increases as we go downstream. So pressure increases as we go downstream. All right, and then we also have what we call the favorable pressure gradient. And this is where dP dx is less than zero, and the pressure decreases as we go downstream. Okay, so those are our definitions that we have here. And kind of the easiest way to look at this, in my opinion, is to consider a converging diverging nozzle. Consider a converging diverging nozzle. And we will be considering incompressible flow. And we'll also be assuming that the flow is steady, okay? And so with this, if we have a converging diverging nozzle, so it's coming like this. So it comes in, converges, and then diverges. That means the area at the inlet gets smaller, and then it increases again. So we have some coordinate system, call this y, and call this x. And I want to kind of bring this into sort of the context first of what we've talked about before. So imagine we have a streamline that's going through the center of this converging diverging nozzle, and let's say we have 3 locations, say 1 upstream, 2 at the center of the nozzle, and then 3 down here in the diverging section. So this is our converging section, and this is our diverging section. It's our diverging section. Okay, so what's going on? Okay, so I'll tell you, to start out with, we have the situation where here on the left-hand side in the converging section, we will have that dp dx is less than 0, which means that we have a favorable pressure gradient. And over here, dp dx is greater than 0, and which means we have an adverse pressure gradient. Okay, and let's talk a little bit about what we mean by this. So let's kind of divide our domain here in half somehow, and then that way I'll kind of keep things going, each on one side and then on the other. So let's consider for a moment. Let's consider our streamline where frictional effects aren't important along the center, okay, where we have Bernoulli should be valid. So if we write Bernoulli from 1 to 2, okay, from this point here to here, from the upstream, the converging section, to the center of the nozzle, in such a case, we will have, Bernoulli will tell us that V1 squared over 2 plus P over rho, P1 over rho is equal to V2 squared over 2 plus P2 over rho in this case. Again, we're ignoring the buoyancy term, or the hydrostatic pressure. And we also have here conservation of mass. And that's V1A1 equal V2A2. And from conservation of mass, we can see that, of course, V2 is going to be equal to V1 times A1 over A2. And since our cross-sectional area here, so say it's a wide channel, so then this height here, this area 2, this is, say, area 1, we know that area 2 is much less than area 1, so A2 is less than A1, and so A1 over A2 is going to be bigger than 1, hence V2 is going to be greater than V1. We accelerate into the nozzle, which is intuitive. What that also tells us, though, is that du dx is what? Greater than 0. Oops. It's greater than 0, which means the flow is accelerating. And what is happening, so again, this is along our streamline. So what is happening then for Bernoulli's? So we can rearrange Bernoulli's equation. So we can say that V2 squared minus V1 squared over 2 is going to be equal to, so P1 minus P2 over rho. So I've just rearranged Bernoulli's equation. And so if V2 minus V1, so V2 is greater than V1, so V2 minus V1 needs to be positive. So that means P1 minus P2 is also going to be positive. So this implies then that, of course, that du dx is greater than 0, but if P1 is greater than P2, that means that the pressure is decreasing as we go from 1 to 2. So if the pressure is decreasing in the x direction, that means that dp dx is negative. So the pressure is decreasing in the x direction, it's negative. And again, this is what we call a favorable pressure gradient. Okay, we can do the same thing for our situation with the on the right-hand side in the diverging section of the nozzle. So we'll write Bernoulli from 2 to 3. And if we write Bernoulli from 2 to 3, same exact kind of idea. We'll have V2 squared over 2 plus V2 over rho is equal to V3 squared over 2 plus V3 over rho. Again, now conservation of mass is going to be V2A2 equal to V3A3. And so now we can say that V3 is going to be equal to V2 times A2 over A3. The area 2 is less than the area 3, so A2 is less than A3 that we've seen here. So if A2 is less than A3, then this quantity here is less than 1. So we multiply that by V2, and that means that V3 must be less than V2. This is really just kind of a Bernoulli review, but it's good to do. So if V3 is less than V2, that means that, so V3 is down here, it's less than V2. That means that the flow has decelerated as we've moved to the right, or increasing x. So if the flow is decelerating as we move to the right, du dx is negative, okay? And similarly, like we just did on the left-hand side, we have V3 squared minus V2 squared over 2 is equal to P2 minus P3 over rho. Again, I've just rearranged my Bernoulli's equation. And now we've said, as we said, V3 is going to be less than V2, so that means that du dx is less than 0. And over here, now we have since V3 is less than V2, what that implies is, as we looked at before, V3 being less than V2 means that this is a negative sign. V3 is less than V2, so that's going to give us a negative term. And so the right-hand side, of course, has to be negative, since they both have to equal each other. If it's negative, that means that P3 is going to be greater than P2, or similarly, P2 is less than P3. And that means if P2 is less than P3, that means the pressure is increasing as we go to the right. And so dP dx is greater than 0. And again, this is now an adverse pressure gradient. Okay, so that's our adverse pressure gradient and favorable pressure gradient. So what is the impact of an adverse pressure gradient or favorable pressure gradient on the boundary layer? So what we're going to do is go ahead and kind of think about that. So let's say we have a favorable pressure gradient. Okay, and again, what does that mean? That means that dP dx is less than 0 and du dx is greater than 0. The flow is accelerating, okay? We're going through our nozzle and the flow is accelerating. So we can think of the favorable pressure gradient. This is on the inlet side or the converging side, and the flow is accelerating as it goes through. So at the center line, the flow is accelerating, but we do actually have friction near the wall in the boundary layer, and so it still has a no slip condition at the wall. So let's think about what the velocity profile is going to look like. So this is y versus, say, u of y. Our velocity profile might look a little bit like, say, this. And it's probably good to draw on top of it the zero pressure gradient boundary layer. So the zero pressure gradient boundary layer is going to look more like this. Okay, so this would be zero pressure gradient. And this black line, this is going to be the favorable. And it should make sense. So the flow is accelerating, so the maximum u has to be greater, so that's the case, and for the favorable pressure gradient. And also, since it's accelerating in the center, we're going to have a larger shear stress or a bigger gradient near the surface. So one of the things that we then want to look at is, let's look at the gradient du dy in this case. So if we kind of call this the top of the boundary layer here for a second, what does du dy look like? Well, for the favorable pressure gradient, du dy, as we go out to the boundary layer, so outside of the boundary layer, the velocity is constant. So u doesn't vary with y, and so the velocity, the boundary layer has to have something close outside the boundary layer. The du dy is to be something close to 0. And then near the wall, we have a pretty sharp gradient that you see here. And so that means that we're going to have a profile that maybe looks something like this. Okay, so the boundary layer, we have a gradient that's positive. And why is it positive? Sometimes it's easier just to go back to plotting it the other way. So u versus y. If our profile looks like this, then what we can see is that this gradient here, the gradient here, du dy that we have, this is greater than 0, and so at the wall it's the biggest, and then the gradient starts to get smaller and smaller as we move, and then eventually goes to 0 where we're, say, outside the boundary layer. So this is sort of just turning our velocity profile on its side. And so this is what the gradient is going to look like for this case, for the favorable pressure gradient. We can also think about what the second derivative would look like. So the second derivative, if you remember, this is related to our curvature that we have. And so in this case, all of this is concave down. So we're going to have a negative, so move this over, so I'm going to have a negative second derivative. It'll look something like this. What does the, just to kind of talk about it a little bit, what does the zero pressure gradient case look like? Well, actually it turns out that at the wall we're going to have a 0, so we're going to do du dy. It looks like this for the zero pressure gradient case. And at the wall, the second derivative is equal to 0, so it's going to go up like this, and of course go back to 0. So this gives you an idea of what the profiles look like for a favorable pressure gradient. Now let's consider the adverse pressure gradient, because this is the one that's actually, let's say, more important, because when separation occurs, that's going to lead to stall and increase in drag. So again, now we'll look at the adverse pressure gradient. Remind yourself what that means for dp dx and du dx. So adverse pressure gradient means that the pressure is increasing in the streamwise direction, so dp dx is greater than 0, and it also means that the velocity du dx is decreasing in the streamwise direction. Okay, so what does this look like? So let's look at our velocity profile. So the flow is decelerating, so u and y, and so what ends up happening is the flow is decelerating, and it's going to start to look a little bit like this. Maybe I'll redraw it one more time just to kind of emphasize it's coming in and kind of doing this kind of a thing. And for our, so if we kind of think about what this looks like, we're going to have, in terms of the gradient at the wall, so du dy as a function of y here, what is that going to look like? Well, and again, I need to maybe do a better job of sketching this. What's happening is something like this. So we have somewhere in here, we actually have an inflection point. And this inflection point for the zero pressure gradient case was actually basically at the wall, whereas the inflection point the inflection point was basically at the wall, because that's where the second derivative here was going to 0. So here we're going to have an inflection point that's above the wall, and so that means that our so the first derivative needs to be 0 there. So we go ahead and, we need to have a maximum. So it's going to look something like this for that. And then if we look at the second derivative, d squared u dy squared, as a function of y, well, at the surface, we're going to have a positive gradient, and then it's going to go to 0, and then back again. So this is because we have this inflection point in the velocity profile with, and we'll say this so far is a weak adverse pressure gradient. And then what we can do is say, well, what if we increase the pressure gradient a little bit more? There'll be a situation now where actually the gradient at the wall is 0, and then it'll increase again and then decrease. So if we go ahead and plot this like I did before, where this is, now we have u versus y, just to kind of make it a little bit clearer. It's kind of doing this kind of a thing. And so here, this is the convex up. Convex up means that you're going to have a positive second derivative, and this is convex down, meaning you're going to have this negative second positive. It's convex up is our positive second derivative, convex down is our negative second derivative, and that's what we're seeing over here. Okay, and so if what the situation happens is that when we have a second derivative here, or sorry, first derivative here that goes to 0 in this case. And so this is, as you see here, so in the weakly, I'm going to draw this again, in our weak pressure gradient, adverse pressure gradient, it's not this. The first derivative is not quite 0 at the wall. But then when we get to the point where we have an inflection point, when we have a 0 derivative at the wall, it's going to again look something like oops. It's going to again look something like this. And when the derivative is 0 at the wall, so du dy at y equal to 0, this is derivative equal to 0 at the wall. This is by definition the separation point. And separation point, if du dy is equal to 0, so what is our wall shear stress? Well, that's mu du dy at y equals 0, or the wall. If du dy is equal to 0 there, then we'll also have the situation where the shear stress at the wall is equal to 0. So this is our definition. So we have either du dy at the wall is equal to 0, or the shear stress at the wall is equal to 0. This is our definition of the separation point. So what happens after that? Well, that's a good question. So after the separation point, if we look at our velocity profile now, so before for the point where we have separation, remember our profile looked something like this. Now what's going to happen after separation is actually the flow is going to go in the opposite direction. It'll be negative and then slowly move back towards what it was in the positive case. So we actually have this negative flow, which we're going to call reverse flow. And this reverse flow is what was happening in the wake of that airfoil that you saw in the video. So kind of draw our two different profiles. So this profile here, this is the profile at separation. And this separation, and this is the profile after separation where we have reversed flow. Okay? So a couple things that are also interesting about this. We can talk about our shape factor that we have. So the shape factor is definitely going to change when you have profiles like this. This looks nothing like the shape factor for our neutral boundary layer, our zero pressure gradient boundary layer. So if we have a laminar boundary layer, and we go from dp dx equal to 0 to dp dx greater than 0, and this is an adverse pressure gradient, going to separation, basically. So to separation. In such a case, our shape factor, h, remember that this is the ratio of delta star over theta. So that is going to go now from 2.6 to about 3.5. And for the turbulent case, it's going to go from about 1.3 to about 2.6. So you can see this change in in our pressure gradient substantially alters the velocity profile, and we saw this. These are the different velocity profiles that we were looking at for the adverse pressure gradient. So given that, let's go back and take a look at our what we were a little bit more at kind of a more physical look at things. So here's another example that I pulled out that has, again, we have a converging duct, and it shows you the different velocity profiles that you would have. So we upstream here, this is your region that is your favorable pressure gradient. This is no pressure gradient, and over here this is your adverse pressure gradient. And you can see what it does. You can see that the velocity has to decrease as the pressure is increasing, and then at some point in time, you know, the flow at the wall is decreasing more rapidly. It's already zero at the wall, so as the pressure gradient acts on it, it goes to zero very rapidly, and we get to this point again here where we have a zero gradient at the wall, and at such a location, that's where the separation occurs. And then at that moment, we're going to have a streamline, which we call the separating streamline. And that's where we'll get this backflow or reverse flow that we're talking about. Here's another example of the same kind of concept. Say we have flow over a cylinder or flow over a sphere. Again, on the upwind side of the sphere, we're going to have a favorable pressure gradient, and on the downwind, we're going to have an adverse pressure gradient. It's the same concept. Before we had a wall here, but the flow accelerates as it goes over the top of this sphere or cylinder, and as a result, we're going to have an increase in the velocity, and then as we move down the other side, the flow is decreasing near the wall, and ultimately we'll have this inflection point, this inflection point that occurs here, and then we'll have du dy equal to zero at the wall, and that's where separation will occur. Again, this is another example of basically the same thing, but emphasizing the fact that a separation streamline that we have here, that's shown like this is the location where the flow can no longer follow the object's surface. It loses contact with it, and as a result, we call it separation. Okay, so some more examples of separation. This is flow. The top figure is flow over a elliptical shape, and you can see that for the most part, you can start out with a laminar boundary layer, and maybe it becomes turbulent, and then separation occurs at these points here. Once separation occurs, then you can see that we have these vortices that form. We call it a vortex street in the wake. Here on the back edge of a cylinder, you can see for these, say, call this 1, 2, 3, and 4. This is increasing Reynolds number. So you can see as we increase the Reynolds number so RE of 1 is less than RE of 2, and RE of 2 is less than RE of 3, etc. Let's just do it. RE of 3 is less than RE of 4. So as we increase this Reynolds number, we can see that we get separation starting to occur at these points that move upstream, and then these reverse flows occur. So we have a clear reverse flow associated with these eddies that are there. So this is this region of reversed flow after separation occurs. So this is really an important concept. Even over these objects, so some kind of important pieces that you'll see is sometimes you'll have reattachment. So here, let's think about we have flow from left to right. We have flow that comes in. At this point, we have a stagnation pressure, which is going to be very high pressure. As the flow goes around, the flow is going to accelerate. The pressure is decreasing. You can imagine that if you think about Euler N, if the pressure goes out, the pressure is decreasing. And so we have pressure here that's very low. And then we have the pressure increasing again as we move out over here. So pressure is, as the flow accelerates over it, the velocity is increasing, the pressure is decreasing, and then at some point the flow cannot hold on to the surface. We're going to have a separation point, some flow reversal, and then we're going to reattach. The flow reattaches. So here, this was separation. and that was reattachment, separation, and reattachment, and that was a stagnation point. And in this case, it was symmetric on the top and the bottom. What you'll notice is this separation and reattachment, these concepts are really important for what we say flow around bluff bodies, where like boxes or different types of shapes, like a car, where we're going to expect this to happen. And it very much plays an important role on what's going on in the flow. But we can also have this happen with streamlined bodies. So here, this is an example of a symmetric airfoil. In the first case, the angle of attack, so angle of attack alpha is equal to 0, and in which case, all we have is basically, we have our leading edge, we have a region where we probably have a laminar boundary layer, maybe a turbulent boundary layer, and no substantial separation, a little bit of a wake that occurs at the very trailing edge. But this is almost all of the drag that we'll see here is associated with the friction on the surface of the airfoil. As we can see over here, we have separation occurring. Now we have alpha equal to, and I'm not sure what the angle is here, but say alpha equal to, say, about 5 or 6 degrees. And then we have separation that occurs. And then we have this separation bubble where we have a wake that's forming. And in the wake, we have a whole bunch of loss of energy because we're taking energy from the free stream and actually dissipating it into heat in that area. Okay, so that more or less is going to cover what I want to talk about today for pressure gradients and boundary layers. What we're now going to start to move into is forces and external flows, so drag and lift. And I think this is, again, a relatively fun portion of the class. I apologize. There was something that happened in the breaking the lecture into 2 pieces, and I'm trying not to have that happen again. Hope everybody's doing well, and we'll talk to you again tomorrow.